So today we have a talk about tree-based methods. It's very interesting set of methods for machine learning, and Maja, who's also an NGS member, will talk about it.
Okay, so hi everyone. I've been here a few days, but I haven't properly introduced myself. And also because I missed the short talks, so here's the one slide for me. So basically I studied mathematics for 3 years, then I studied molecular biology. I did my bachelor's and master's in molecular biology. Then I did a PhD in bioinformatics. And during the PhD I was working on various datasets because we had a small group, so thankfully there was nobody else to do it, so I did it, which was great. So I did like RNA-seq, nanopore, normal Illumina sequencing, I did assembly, like whatever, metagenomics, HIV integration, whatever you can think of, probably I've done some of it. So now I am working in C2I Genomics. It's a company that's working with cell-free DNA and trying to do we're working with the whole genome sequencing of cell-free DNA and looking if there's residual disease from tumors. And in the free time, so I have a husband and I have a daughter, and the daughter is little, she's 1.5 years, so there is not much free time, but in the free time that I do have, like it's 6:15 a.m., so I'm doing CrossFit or running, and that's basically it. That's my whole life, every day. Okay, so I don't know why, I really like the decision trees and random forests, but not that much that I will talk about it all the time, but somehow in the end I always use it and I do talk about it all the time. So I think it's appropriate that I'm here talking about it. But yeah, so I'm not going to force you to use it like the other way around, but let's see what it is. So how many of you know or have worked with random forests or trees of any kind? Quite a lot of people, great. Okay, so basically I will start easily, but then in the end it will get progressively better, I would say, and then I will show you the few examples in the end actually. Yeah, you see, I have here in the beginning, so, sorry. So, yeah, we will start with the decision trees, then move through bagging and random forests to boosting, which is kind of state-of-the-art, kind of now, and something that's called BART. And then I will show you my examples over the years, what I've done wrong and what not to repeat. So I think this is going to be something interesting, maybe. Okay, yeah. When we talk about decision trees, this is the first picture that comes into my mind. Basically, we have this game, and then you're supposed to guess who this person is. And what you're doing is you're actually, the first thing that you want to ask, unless somebody tells you not to ask this, is whether this is a male or female. So you ask, is it male? And then basically you lose half of the people, because half are male, half are female, which is great for you, right? And then if, let's say that this is something that the other person has. The gender is male, yes, okay, then you ask, you see that there is quite a lot of bald people here, so you ask, is he bald? And then the person says yes, the person says no, and, yeah, sorry, the person says yes, and you're like, okay, from the bald people, who else do we have? Okay, is it Bill? Yes, great. Or does he have glasses? No, okay, great, it's Bill. So basically, I'm just oversimplifying things here to explain to everybody that we do have some, even in this most simple example of a tree, let's call it like this, a decision tree, we did have some variables. The variables were gender, baldness, length of hair, glasses, or whatever. And we did have a set of observations. We did kind of perform the classification. The only class that we were interested if this is a Bill or no. So this is kind of a classification tree, and the only reason is that I'm putting it here is to introduce you to the terminology. So basically, what I want you to get from this slide is that there are some splits, and these splits are called internal nodes, and what is in the outside is leaves, or terminal nodes, and all the leaves basically just have the mean of observations that are here in this leaf. So the value that represents the leaf is the mean of the observations, or the most occurring class, if it's classification, that represents the observations that are in this leaf. Okay, this is very clear, right? Okay, so let's try to build our own tree in a very, very known example. So this is, like, I think, perfect example for this. So this is the data set with hitters. It's like a baseball data set. So it has baseball players, and here you see only two variables. The X variable is how many years each of the player has been in the league, okay? And the Y-axis is the number of hits that the player has scored. So dots are the players, and the color represents their salary. You can see here the color doesn't represent their actual salary, but the logarithm of their salary. So, for example, this person here, who is like very red, he has the salary e to the 7th. So that's quite a large salary, right? And then this person who is blue, or all of these people who are blue, they have salary 2 to the 4th. E to the 4th, whatever. Okay, so basically, if somebody was going to show you this and tell you, can you make classes that best represent this data set? So somehow use years and number of hits to tell me how much should I pay a player, and divide them into low income, mid income, and high salary group. So how would the splits have to go? So you see that the blues are focused around here, then you have the greens around here, and then you have the yellows and reds here. Is this visible, right? It is, because this is the perfect data set to show it, because not all data sets are like this, of course. But yeah, for example, this would be the perfect tree to represent it. So just to say, here we have the first division. The division is divided by the years they have been in the league. Everybody who's been in the league for less than 4.5 years is here, and the mean of all the observations, mean of all the log salaries here is 5.11. Okay? Then the next one is here. The players who have been in the league for over 4.5 years, but have less than 120 hits, okay, their log salary is 6. And the rich ones are here, and their log salary is 6.7. Super clear. Okay. So how do we actually build a tree? Well, in general, like, it's very easy. You just divide your predictor space. In this case, it's just 2 predictors, right? So we divide it into distinct non-overlapping boxes, which basically looks like this. So if you're trying to divide something into 3 boxes, you're just trying to think of all the possible ways that you can divide this into, well, 3 boxes, right? And then, how do you decide which division is better? Like, is this one better or this one? How do we know?
Which one is like most?
Can you speak up?
Which one is like most homogeneous? Like all the dots are similar.
Okay, and perfect. So the way to formulate this, literally by formula, is like to say for which of those divisions is the sum overall divisions of the residual sum of squares the least. Okay, so that's it. So we do have a metric by which we can decide which division is better. Okay. So now, since we have 2 variables, it's kind of very easy to understand like what is the best split. But let's imagine that we have 10 variables and we need to do all the possible splits. Now, is this feasible? Like, do you want to do your tree like this? So how many possible splits there are here? What does this depend on? Okay, so it depends on like the number of possible splits between the dots in each of the variables, right? Okay, so the time of the possible splits in this variable times this variable is all the possible splits. So it means that when you have 10 variables, it will be number of splits to the 10th. which is too large and nobody's going to do that. So what do we do?
Reduce dimension.
What?
Reduce, like sometimes physically to reduce the dimensionality.
There is an easier way to approach this. Okay, maybe there's one way to go. Why not? Sure, it will give you better results, but this is not. You're not using only trees to do this. So actually, what they did, I mean, the way to do it usually is to do the gradient approach. So just take the first best split, and then don't decide among all best possible splits for two variables, but instead, okay, let's do it like this. Because I did have like 6 slides which do this, so to use them. Okay, basically, so you do this, and then you calculate the RSS here plus here, okay, do it here, blah, 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 and so on. You do this for all the possible variables, for all the possible splits, just on one variable. And then you take the least one. This is your first split. Beautiful. Then, when the first split is set, you decide on the second split by having the first split in mind. So, with this being the first split, split the rest in a way that the RSS in this is minimized. So this is a greedy approach. It doesn't. So you can also do this again. It's fine. But the point is that you should take a look at all the variables given the split. Okay, it doesn't guarantee you that you will get the best possible tree in the end, but what you will get will be a tree. Let's call it like this for now. Okay, yes. So the details of building a tree, I think it's pretty clear, and it's pretty clear that so how do we predict the response for new data? For example, now we have a tree. How do we predict? Okay, so I think it's a very easy question. This is why nobody is answering. So let's take me for an example. Like, I'm the thing to predict on. Like, I have less than 4.5 years in the league, definitely. I have less than this RBI, definitely. I have less than 82 pull-ups, whatever, definitely. So my paycheck should be e to the 5th. And these poor guys here, okay, lower salary? Nice. So the problem with trees is that they tend to perform badly, and they tend to overfit the training data that you have. So what is this called? The variance is what? Okay, so this is called high variance, like they have high variance. Okay. So how do we solve this?
Consolidation.
Yes, okay. We'll get to something similar to this, but for the trees they had a better idea. I think better.
Random forest.
Random forest. So, but how do we solve this in one tree? Well, what can we do to this tree to reduce its variance?
The steps of dividing.
Yeah. So, what did you say? Sorry.
Limit the steps.
Limit the steps. Yeah. So actually, instead of limiting the steps, the depth that you're trying to do, it's better to build a very big tree and then to trim it back, because yeah. So this is actually what they do. So it's really very logical. And how do they do that? Maybe this one I can show you. Does not like that. Yes, the way to do it is to pay the cost for complexity. So you just add, so this is the RSS, right? And then you add this alpha parameter, and then this is the size of the tree, the absolute value of the size of the tree. So you're adding some cost to the size of the tree. Big trees will have bigger cost, and that's it. And you're actually using the cross-validation to choose the alpha. So this is how they're getting the optimal trees. Cool. Yeah, so for classification, since we don't have RSS, we need to use some different measures. And what is used is classification error rate. Well, it's not used because it's not sufficiently sensitive. And it's really like jumping between like you change one observation and the answer jumps. So what they use is this. Have you seen this before? Does anybody know how to explain this formula? Okay, yeah, probably because I haven't explained what is what, so maybe that's why. Okay, so PMK would be the class which is appearing the most in the kth division. So maximum class in the division is the probability of this like class. And then, for example, if all the observations in one class are this class, then this would be PMK would be 100 or 1, and 1 minus this would be 0, and then all of this would be 0. So the idea is to have this as low as possible, and then this is better. So this is absolutely the same as this, except for you don't have like 1 minus this, but you have a logarithm, but the thing is the same, it just behaves a little bit different. Okay, so this is what we do for classification. Whether trees are better than linear models, whether any tree-based method is better than linear model, it really depends on what kind of dataset you have. So it's commonly used the heaters dataset because they're nicely formatted into boxes. So if something is a box, you are more likely to perform better with a tree than with a linear model. Okay. But it's never either of those, it's always something in the middle. Okay, so advantages of the trees is that, for example, when you're working in a company and you try to do something very smart and some really cool model, and the performance of this model is amazing, nobody will use it because they say, yeah, we can't use this model, like how do we explain to doctors why do we exclude these samples? And I tell them, well, you just show them this model. And they said, no. They want to have like 2 rules based on which they will exclude like some patients. Like, okay, let's do some kind of a tree-based model. And then you have to do trees. But that's the only reason why you would do them. Otherwise, I mean, yeah, they mirror human decision making. They're easy to explain to people. People understand them. This is very, very important. Easy to interpret, and also can handle qualitative predictors. But in theory, like all of this falls into water because their performance is just not good. So they kind of suck. Okay, so that's a disadvantage, but hey. Yeah, so what can we do? We said that the problem is that the variance is large. So how can we reduce the variance so what does it mean that the variance is large actually? It means that when you take a different training set, you will get a different tree. And the prediction on this tree of some test set will differ largely than the prediction on this tree. So this means that the variance is large. If you have, does anybody, based on this, have a way to reduce the variance?
We can pick many trees on sample data and average the response.
Yes, so this is exactly what is done, right? Because averaging reduces the variance. So in theory, if we did have like multiple training sets, you would just pick new trees and average the response, and this will give you less variation in the response, which would be better. So that's actually what bagging is. Okay, so the problem is that we don't have new training data. How do we deal with this? Like, has anybody heard of the Bootstrap? So what does the Bootstrap do?
Replacements.
Okay, why does it work?
We replace some observations by another from each data set and try to use our method. Do it very many times, 1,000 or 10,000.
Okay, so basically it's a way of generating new training sets from the training set that you have by sampling with replacement. It's important that you use sampling with replacement because then each observation has the same probability of being chosen as in the initial set, which is a good enough representation of the population because it was sampled from some population. So this is why it will work. And this is how it looks. For example, if you try to make a bootstrap, if you have a small data set of 3 observations, okay, of X and Y, and if you try to make a bootstrap out of it, this is how you will do it. For example, in the first bootstrapped sample, you will choose the observation number 3 2 times, you will choose the first observation 1 time. In this second one, you choose all of them in different orders, so basically you choose is the same. And in the third one, you randomly chose second one 2 times and the first once. Can you, like, what can you see that is written here? Also, yes, beautiful. So on average, between all the pairs of the training sets, you will have 2/3 of the observations which will be absolutely the same. And 1/3 of the observations will be different. So is this a problem? Like, what do we do now? We said we wanted to average over the trees to reduce the variance, right? Okay, so we made ourselves new training data. Fine, a lot of it. Like this can be 1,000, whatever. And then on each of those fake bootstrapped training sets, you make one tree. And then you just, when you're trying to predict something, you predict on each of those trees and you average the prediction. So will it be a problem that you have, so yeah, this is how it goes. For example, on the new test set, you get a prediction 5.2. On the second one, you get 6.1. Here you get 5.5. So the 5.6 is the average over those predictions. For the second row, you get average 5.5. For the third row, you get 5.6. So you can see that whereas the variance is not reduced among the trees themselves, the averaging reduces the variance between the tree observations. So it means that you're more stable in your predictions, which is great. So actually, it doesn't matter that you did have like 2/3 of the data overlapping, you still get more stable results. Okay, so it does work. Is there any kind of problem with this?
There are no models.
You need to speak up.
It's not manipulable now. It was, like now it's regulation that simply say what are the rules. Because we have many rules and we have
It's not a problem. So how would you create a rule based on this? You just add them all together. So you say, I mean, because, yeah, I agree that it's not as interpretable now. You do have, actually, so in the trees, the good thing was that we had the variable importance based on the first split. First variable was the most important. And actually, this length, it tells you what is the drop in the RSS after the split. So you know how important it was. But, okay?
So maybe the problem is like a test set isn't really independent since it was trained based on inference of the same data.
Okay, but we're not using it as a test set.
Okay?
So we have a new test set.
Okay.
So the trees are correlated because they use the same predictors every time.
And why is this a problem?
For example, if we have a predictor which is really important, the first split would always be the same.
Okay.
So the variance isn't really, the reduction in variance isn't as big.
Yeah, so basically you would always get the best split chosen for the same variable. Always one variable will be chosen as the best split because you always include it in the data. Okay, let me just see. Yes. So, okay, we can jump around a little bit. Let's do it like that. So since we always have all the variables, like maybe the most important one will. So why is this a problem that we choose one variable all the time? Does it mean that this variable is the most important, or we are not sure? Like in which cases aren't we sure that this is the variable which is the most important? If we are choosing it all the time as the first one, it must be most important, right?
And collinearity, if some variables are highly correlated.
Yes, exactly. So you want to give some others a chance to stand up. So maybe if you choose two different variables, their performance would be better than just this one. And by choosing this one, if it's correlated with those two, you don't give them even a chance. So that's the problem. This is why the performance of trees is always bad, because they always use the same data, and you never give them a chance to choose different variables. Okay, so how is this solved? Well, obviously, since the next step is random forests solve this problem. And how do they solve this problem?
You can subsample some features.
Exactly. And they actually subsample these features every time they do the tree. So let me just check where am I in the presentation, because who knows. Okay. So yes, so actually they just randomly select m out of p possible predictors for each split or for each tree making. And this is German, the m trie parameter.
Thank you.
You're welcome. Okay, so actually, but there is something interesting about this. So, for example, when you do, it's really important, like how many variables you let at each split, because, for example, when you do regression, you only take like square root of the number of variables. If you have 100 variables, you will only take 10 at each split. But when you do classification, you take by default like the third of all the variables. So this is something that can really highly impact on your result. But just have it in mind. Okay, so yes. Now let's go back to this. So we said that in the random forests, we are not taking all the predictors and we are not taking all the data. So there is always some data which is left out. And this data which is left out is called, well, left out data, right? But you can use it to estimate error on this data, because each time you're using 2/3 of the data in the, I mean, not 2/3. So each time, yeah, at random, you're using 2/3 of the whole data set, but you have the observations that you didn't use. So you can just test your error on the observations that you didn't use, and this is called like out of the bag error estimation. So this is quasi-test set. While you're doing the random forest on the full set, you get quasi-test set error estimation. Is it clear how this is calculated? Okay. Yes, the problem is that it's not that accurate. So while it is a good, I mean, it's a better estimator than the training error, it's not really a good estimator. It's not a perfect estimator for the test set error. It does have some kind of a bias of its own, but what you can use it and what it is used for actually is choosing the parameters. Because you see that, oh, okay, sorry. So this is the test error on the bagging, this is the test error on the random forests, and these are the out-of-the-bag error estimations for bagging and random forests. So you see that we are a little bit optimistic with out-of-the-bag error estimation, but it's not a problem, because what we're using it for is to see when does the error stop being, jumpy and settles down. When it settles down, this is when you know that you have optimized your parameters that you have in the random forest. Which parameters do we have in the random forest to optimize?
Number of trees.
Yes, and?
Maybe M and P.
Yes, M is the number of predictors you choose at each split, and the number of trees. So you get this basically for free when you're doing random forest, because it's easy to do it with the out-of-bag error estimation. Okay. This is it. Another thing we do is to determine which variables are important. So somebody said that there was no explainability of our model now, because we don't know which is the most important variable. But actually, because we have a bunch of trees and things like this. But since we don't have this, we don't choose all the predictors all the time, we can just look at the errors when our predictor was chosen, and looked at the errors, out-of-bag errors, when our predictor wasn't chosen, and to check this difference. So this is called variable importance, but mean decrease in RSS, or mean decrease in GNA index, or mean decrease in whatever you're using to estimate error. So by the decrease in error, you can see which variable was most important. Okay, is this clear? I love that my lecture is after lunch. This is wonderful. And after a party night. Great.
We have those.
Okay. So, yeah. I mean, it's all good with the random forest, but the problem again is that you're fitting very hard at the same time because you're fitting on the entire, so you're choosing your parameters and fitting the trees based on the entire data set, I mean, based on the subset of the data set, but all at once. So you can go like overly direct at things. Okay, so how they managed to treat this is by boosting. So boosting is a really clever method, but it's super simple. So basically what's happening here is that each time you fit a tree, you fit some tree, like in the random forest, you fit some tree, and then you say, okay, but let's, step back and weight this tree with some, so shrink the estimations on this tree by some very small number. For example, you just take penalty, or you shrink your tree by lambda, and lambda is usually really small, like 0.01. So you take just 1% of this prediction, and then you fit another tree to the residuals. So you're just trying to explain what was not explained. And then again, you shrink this prediction to some small lambda and add it to the first tree. So you always just explain the unexplained part and shrink your predictions. And by adding them all up, you'll get a much, much better prediction. I mean, much, like few percent improvement, but this is still a better prediction. Okay, so is this clear? Like, this is the state of the art. Shrink the trees. So, does anybody see a problem with this? In the end, you get how many trees? Huh? You get one tree, actually.
But in the end, yes.
Yeah, in the end you get one tree, right? In the process you used a lot, but in the end you get just one. So wouldn't it be better if we had more trees, because then we could reduce the variance? This is the next step which we did previously. Yes, this is the next step. So after boosting, I will go back to this, but I just want to jump. This is now the state of the art. It's like, let's use more trees. And let's also, instead of lambda, use priors, because why not? So this is what they do. They use priors, which are based on the depth, on observations, and the deviation of the residual noise. And then what they do is not fit one tree, but fit a whole bunch of trees in the first iteration. And then they protrude these trees, by doing this. So they shake up the trees by adding some noise. You can add noise by removing the branch, adding a new branch, or changing the prediction of the values that you put inside, like of the, changing just a little bit your mean that you predict for each leaf. So these are the three things that you are allowed to do in this method. And then you repeat this like many times. And then you burn out the first 100 models, like the first 100 iterations, because you say, okay, but in the first 100 iterations I wasn't that good, my model didn't converge yet, so I'll just leave that. And then you just take the rest of them, and from all of the rest of the trees, you now do average, and you can also do confidence intervals because you have so many trees, you can do whatever you want. So basically this is now the state of the art. I wonder where this is going to go. Do random forests on the parts. Yes. Okay, anyway, so the performance of this is of course, again, better than even the boosting, but as Leo said yesterday, we still don't know where this will go, so let's go back to boosting. So let's pretend that boosting is now the best thing that we have, and it's actually really, really good. So, but it does have some parameters which you need to optimize. These are the depth of the trees that you are allowed to build at each split, and then the number of trees, and the learning rate, and all of this can be optimized by cross-validation. Yes, but actually the problem in the boosting was that if you select high enough number of trees, you can overfit. So your results might be only better because you overfit and not because they're really better. So this is why they thought, oh, maybe we reduce the variance. Yes. Okay. So this is it. There's no, I mean, the devil is in the details, but this is kind of the general theory behind trees. So do you have questions about this?
Can you repeat in the bar when you add this noise, perturb it? What happens next?
Okay, so in it, you first create a bunch of trees based on something, based on your data, let's say like in random forest. And then you either remove the branch randomly, either add a new branch randomly, here, wherever you want, or change the value of the predicted, value that you predict for the group in some of the branches. So these are the three things that you can do to shake up the data a little bit. You do it randomly, and then again you repeat the building on the residuals, and you shrink it based on the prior instead of the lambda. Okay, and the prior is, well, you can take whatever you want, but it's usually has to do with the depth, the observations that you are the predictions, and the standard error of the residual noise. So you just shrink it based on prior instead of lambda, and you add some additional noise each time you do the tree. And you burn out the first 100 because they're not good anyway. And we know this because of, they were not good in random forests, they were not good the first few in the boosting, which is very similar to this, so why should we use them? Well, just not. Okay. Good. Then we can go to the examples of what to do and what not to do. Okay. Any more questions?
What's the learning rate as hyperparameter?
So it's this. Each time you do boosting, you shrink your tree by lambda. Lambda is the learning rate. And then you need to optimize the lambda. Because you make a tree, and then you shrink it, add it to the model. Make the tree for the residuals, another tree, shrink it, add it to the model. Residuals, shrink, model. So this shrinkage parameter is the learning rate, basically. How much do you trust each tree that you add to the model? Or how much you want each tree to update your model. Okay, other questions? Okay. So for the examples, I have 3 examples. First is something I did for my masters, so please don't judge. But this is how it went. I don't know, I got a bit lost there. Anyway, I got 60 patients with liver cirrhosis and healthy people, and I got all of their genes. Somehow it ended up that the genes were observations, because why not? And I had 6 million or 630,000 genes for the patients and 600,000 genes for the healthy people. Okay? So it looked like this, basically. These are genes, and you know that this whole block is one person, and all of those are its genes, okay? This block is another person, and all of those are its genes, blah, blah, other person. All of the blue ones are patients, the red ones are healthy, or vice versa, whatever. So basically what I did is since genes were observations, I actually calculated some of the variables based on entire patient. So this means that, okay, wait. This means that, for example, I calculated enrichment, M and A, and some other statistic, and different levels of enrichment. But you can, if you don't know what this is, you can just imagine that I did ranking of genes within each patient and use this as a variable. Okay. Then, of course, I did have the training set, which was 75% of all the observations, and I had the test set, which was 25% of the observations. And then my out-of-bag error was 10.5%. So what do you expect? And my prediction was whether some gene was based on the variables, was it connected with a healthy or healthy or patient is basically my prediction. So do we expect, based on this setting that I show you, that the error on the test set would also be 10.5%?
Since you calculated some features based on genes, you reduce the data leakage to the out-of-bag error, so
yeah,
it will be higher.
Of course, it was 30%, which was still better than random. So I was like, oh, okay, I can work with this. So basically, what your name said, thank you, is that I calculated some of the features for all of the patient, so for entire patient, and then I divided my data set into training and test. Come on, that's just double dipping, right? You've seen the data already, and then you say, okay, you now go for the training. So this is very, very common problem, and you will do it for sure. You won't be aware that you're doing it, because it's very tricky to know what exactly might influence your data. It's easy when you have just one data set or relatively small data set, but when you work in a company and you see other people doing this and you tell them, I think the test error will be lower, they say, you're here for a very short time, and then, the test set is not as low as they thought, and then I'm like, okay, we might want to do it like this. Yes, so it's the same thing everywhere. So it's really something that you have to have in mind. So what would be a good way to solve this problem then? How could I, if I did want to leave this architecture that I had, how could I then divide the training and the test set? Who said this? Yes, repeat.
By the patient.
Exactly. So leave some patients as a training set, or leave some as a test set, good enough. Okay. Actually, so why this happened is when you get new data, and if it has some kind of a, maybe batch effect, but maybe just batch effect, like for a different population or something like this. If you get new cohorts and you get new patients, and then you have multiple levels of this kind of structuring that you're not aware of, this is what might cause the problem for you in the future. So just remember that, if you get a too good estimation of out-of-bag error, it's probably wrong. So probably try to make it worse before you show the bosses. Otherwise, they will make a big deal out of, lose a lot of time. So don't do this. Yeah, don't calculate something and then split, but first split and then calculate whatever you want to calculate, and that's it. Okay, second example, beautiful. Now we know better, right? Okay, we apply random forests on high-dimensional biological datasets containing expression measurements for 4,700 genes measured on tissue samples from patients. So we had 350 patients. Each patient is one observation. So far, so good. And then genes are columns. Genes are variables. We choose a set of 500 predictors that have the highest variance in the training set and build random forests to predict cancer type. Are we cheating? Now some of you are thinking, oh my god, I did that. So is this okay?
No,
Why?
because we have 500 predictors and that's probably a little bit too much.
Oh, that's not like, I mean, you had 3,000 and you had 4,700, so to start with. So now you're just, okay, so you're saying we should go with 50 here.
Probably.
Okay, so basically this is, the only wrong thing about this is that we chose too many predictors and we can choose those with the highest variance in the training set, but choose less of them.
That's what I would do.
I agree with you. This is completely fine. If you did this, you're good. Like, this is not bad. So why is this different than before? Huh?
Because you used to do it on the trainings. So
Exactly.
you don't have any confirmation.
Exactly. So you're fine. And also you're not checking the labels at all. So you're just checking the variance of the predictors. So you're very, very good. Okay, and the third example is actually like from 2015. You can see this is German and this is me. And actually this is how we met. It was in a summer school in Croatia. And we were there for 2.5 weeks, so this was really nice. I hope that sometimes we can organize such NGSchool because it was really, really cool. Okay, so basically what we were doing is we had expression data for 20 tissues. It had like 10,000 probes, and the probes were like variables. Tissues, whatever, good. And then we wanted to select important probes to predict whatever, some 3 different things. So each of them we predicted separately. This is not important what we were trying to predict. The important thing is that we had probes and we were predicting something, that's it. We decided, like since our goal was to check which probes are important for these predictions, like to check genes which are important, what we did is we said, okay, we have random forests. Great, they give us variable importances. So I think this is something we can use, definitely. But also let's, try the linear methods, like the linear regression, why not? Like it's there. And the MIC, which is some cool something, whatever, you just calculate it and it gives you something. Perfect. So then we did this. First of all, for one forest, this is what we got. Like we got that this probe is very important, and then this is the second one is this one, blah, blah, blah. And we were like, okay, we are getting somewhere. And then you run this again. Since it's random, you don't get these probes at all. And then you run it again, no probes the same. And then basically, we did this a few times before we understood that they won't be appearing so often as we thought. So, do you have some, I don't know, intuition what we might change that we get more similar probes in one random forest run?
Increase, yeah.
Increase?
And
M, yes. So increase the number of predictors you choose. Why?
because in each batch we will have much upper level, so a bigger level of features and
higher chance that those will be in the set that you will choose from. So higher chance that they will be chosen again. Okay, great. It took us some time to do this. Actually, it took us like a few days. And then what we also understood is that, I don't know if you got, okay. So basically, yeah, we went a little bit around this. We thought, okay, but let's just calculate p-value for each of the predictors, because why not? We can do that. So by permutation test. So we would permute our labels, and then we would see what are the importances for each of the probes. This is the, how do you call it? The black thing. And then, if you don't permute, if you just get the random forest normally with unpermuted data, but 1,000 times, this is, 500 times, this is how your predicted importance for this variable would be. And then you see that this is really important based on this p-value, which is calculated by permutation test. And then you can score each of the probes, which is cool. Like we added p-value to random forests. It was really nice. The only problem was for one run of one random forest, it took us 20 minutes. We needed to do it for like 500 random forests for different variables and things like this. Yeah, so it took us some time, and in the end, there was this one other guy who told us, oh, there's a package that does that. Yeah, basically. So first of all, we understood that R, I like it, but I don't, necessarily like all of it. The problem with it is that this was the package that we used was made in a way that if your variable you're trying to predict is a factor, then it would automatically do classification, and then it would automatically choose 1/3 of the predictors at each split. But if it wasn't a factor, then it wouldn't, and it would think that you're trying to do a regression, so it would only use square root of predictors. So this is why we actually weren't getting enough predictors, because this wasn't a factor. Okay, why not? Yeah, so yes, so we updated the formula. In the random forest you can do that. You can say, okay, use classification. And we also found this other package that does all of this in like 10 minutes for everything, so we lost a bit of time, but gained a lot of experience. And this is something that you never forget. Yes, and also we did do the linear regression, which does have the p-values, which were the same or very similar. Like the top 20 predictors were very, very similar, and the top 3 predictors by our super random forest method was the same as the linear regression. So, which took enter and done. Yeah, so it was like this. The conclusions. Be careful when you're selecting variables not to introduce biased or leaked data. You will do it, so make sure that you didn't do it. It's a better way to put it. Do a valid cross-validation, so split, then do whatever. Check your results in a sense that if you think that they're too good to be true, they are. Try linear regression first. So honestly, it's not about the model that you're using. You can use deep learning, but the only reason we are not using it is because it's too slow. So why would you want to start with deep learning and wait for 3 weeks when you can start with linear regression, check that the results are okay, and then make them better by engineering features, by making the representations better? Because this is the entire smart part of the modeling. It's not what model you're going to use, it's how you're going to represent your data and how you're going to do the feature engineering. Okay, and then try some simple approach, or at least the fast approach. It doesn't need to be simple. You will definitely make mistakes, and just Google and read the manual, because I don't know, who would have thought that in the manual it stated exactly what the package does, Okay, so basically that's it. Thank you.